Okay, so without much further ado, we are very much looking forward to have Angjoo Kanazawa as our next speaker.
Right, thank you so much. What a huge room. I hope my voice is great. It's really nice to see Alan start with analysis by synthesis, because he was actually saying it's not popular, but I would argue that a lot of the current approaches, like NERF is, for example, an example of analysis by synthesis. And actually much of my research uses the concept of analysis by synthesis, and it will come up. Okay, so this is a generative model workshop, and I'm sure you're going to hear so much about diffusion models. And it's all the hype because you know, generated images never looked this good. So this is one of my favorites. It's on Reddit. It was on Reddit from some Redditor who was using a custom stable diffusion to generate a Wall Street trader in like a beach or something like this. And I mean, like, look at this, like the quality, I mean, the compositionality of the waves and the legs, I mean, it looks really, really good. Okay, and so I hear that there's a lot of concerns about these large models. And I want to first say that, you know, don't worry. This is really an opportunity for us to do better work. And in fact, tomorrow we're going to be talking about this topic at this workshop called Scholars and Big Models, How Can We Adapt, in this huge room, which I'm not so sure it's a great idea. Anyway, but why? Because in computer vision, we're always solving inverse problems, especially you're doing a 3D understanding like I am. And in inverse problems, you're always maximizing the posterior of the parameter. You're trying to get the parameter that maximizes your current observation. Okay, and if you're not a Bayesian, I can write this in a more English terms, where you have an objective where you're trying to minimize the data term as well as the prior. Okay, so what does it mean that these generative models, like diffusion models, are really getting really good and easy to train? Well, it just means that we have really good priors to use in these problems. And today I'm going to show a couple of examples of this type of work. And this really flows naturally to these really cool works that has been happening, like dream fusion and score Jacobian chaining, which distills 2D diffusion models into a 3D model. And I'm a really big fan of these types of approaches because they're, you know what, they're really learning from single image collections. And I'd like to do a throwback to one of my old papers where we try to reconstruct birds and kind of look at it in this perspective. So in this paper, the idea was to look at lots and lots of images of birds and then learn a model of what bird shapes are like. Okay, and then once you have this model learned, at test time, you can take an image, use this idea to reconstruct a bird from a single image. But in this kind of context, what's happening today is that instead of image collections, we actually have a diffusion model. So now that's gone. Instead, you can literally sample from a stable diffusion conditioned with some text like birds or, you know, like a specific types of birds or anything that you want. This really is what's kind of happening in dream fusion. And I want to use this analysis to give a very intuitive idea of how things work, because that's how actually we're going to do a lot of the works that I'm going to talk about. So let's just go back on this approach. So given the input image of a bird, we were reconstructing some kind of 3D model. In this case, it was a mesh. And then we would differentially render this and then get an image out. And the objective of this network was really, does the rendered image look like the input image? So this is really a classic case of analysis by synthesis. And someone was asking, you know, how is the optimization being done with neural networks? This is like a nice example where you can just do this. Okay. And let's just, it doesn't exactly matter what the 3D representation is, because nowadays this would be a NERF, and the differentiable renderer would, of course, be the volumetric renderer. But let's conceptualize that away, and then look at the intuitive view of dream fusion or SJC. When you're trying to optimize a 3D variable, in this case, we actually don't have any of the input images anymore, but you're still optimizing a 3D representation, which is going to be rendered into an image. Of course, we don't have this guiding input image anymore, but instead, what we're going to do is take this image, add some noise, and then send it to your favorite denoiser, like your diffusion model. And the denoiser is going to output an image, And now you're going to guide your optimization with a term that says, does the rendered image look like the denoised image? Okay, this is really essentially what is happening in Dream Fusion. And the losses are derived in the gradient form, but once you write it like this, you can really write it as like a loss on diffusion as, you have a current optimization, X, and then you're going to diffuse it, denoise it, excuse me, the dxt comma t, because there's like a time, that you need to use for the diffusion models. And then the xt is, you have to diffuse it with noise, and you can do it however you want. And then there's also a no grad involved, and that's really easy. Oh, by the way, I also want to credit Sparse Fusion for this kind of alternate notation of what's happening, because I think it really helped me understand what's happening. The no grad also makes sense because it's more like you want to optimize this parameter which creates an image. Okay, and it's more like somebody gave you an image which is a more realistic version of that image. It's fine that that comes from the earth or the heavens, and then you don't really backprop through it. It doesn't really change the fact that you want to go in that direction. So it makes perfect sense. Okay, so with that, I would like to talk about some of the works that's happening in my lab that is using 2D and 3D generative models for 3D scene editing. As well as, this is a super new work that we just put up on arXiv like 3 days ago, reconstructing people in close social interaction. So 2 different domains. So let's dive in. Oh, okay. So I'm sure you've heard of NERFs. Look at this results from Block NERF, which you can reconstruct San Francisco's famous locations from these Waymo cars. And we also made this open source project called NERF Studio. I'm going to be talking about this later in a workshop at 11 or something like this. But okay, so we have all of these tools that allows you to capture these 3D scenes in a really photorealistic and a much simpler than previous photogrammetry approaches. And so let's capture some scenes. So here is Frederick, who's a visiting student at my lab. Who's also going to be my postdoc. So we got this Frederick, and now what? What do you really want to do with this? Of course, not only do you want to capture, but you would really want to edit the 3D scene and in a way that is consistent with the underlying 3D scene. So here are some examples. And the interface for the editing is a nice interface for this instructions, which I'll get to it more. But this approach, you can say things like turn it into a clown. It can also change moderate amount of geometry, although, oh no, I see. Okay, apparently I'm not sharing. Uh-oh. Okay, there you go. Thanks. All right. Okay, I was showing this video. There you go. Yeah, so here are some of the examples that you can do. Adding context, content in the context of the edits and so forth. Yeah, and then because it's also using diffusion models, it also knows about these pop culture ideas of what they look like. And here are some pretty significant geometry changes. There's still a lot of challenges to be done, but okay, so how do we do this? So this is the work led by Ayan, Matt, and Alyosha, and Alex Solinsky in my group. Okay, so Dream Fusion is a nice, really example of creating from scratch a 3D scene that distills to the diffusion model. Okay, but this is unconditional generation, which is great. And maybe if you want to completely insert a new object in the scene, that is great. But often you want to edit an existing scene. In those cases, there's also nice works by Andrea Vidaldi's lab and Vincent Sitzman's lab that also can select locations and then edit them. But these tend to be regional specific edits, like changing the color of the flowers. And also there's another concurrent work that actually edits NERF scenes by using clip features like in the textual descriptions. And so the difference is that, we would like to do a contextual edit. Not only do you want to change the color of the tent from red to blue, but you also want to say things like, make it look like it just snowed, which requires editing multiple parts of the scene. And I think this is a really exciting direction that takes advantage of the power of 2D diffusion models in 3D, because traditionally 3D editing is a very challenging task. And it actually can incorporate all of these contexts from the priors that it has learned. And so for this, we really rely on instruction, following the work of Instruct Pix to Pix by Tim Brooks and Alex Walensky at Berkeley, where the idea is to given a 2D image, give an instruction. And then this is key. The instruction has nice two benefits. One is that instruction is succinct, and it really only describes about what you want to change, as opposed to descriptions, which require you to describe the image and then change the content. So you don't want to be going like, oh, there's a woman riding a horse in a green background, and then I want to change the horse to a dragon or something like this. Because describing an image by text, I think it's a great, great data that there's image and text, but really there's a lot more in an image than a couple of sentences. Another benefit of Instruct Pix to Pix is that it's image conditioned, meaning like the diffusion model takes in the image, so it can preserve the existing content a lot more. Okay, so the approach really is simple. So we already have a pre-captured nerve scene, which is by definition 3D consistent. And now on all these images, we're going to take the current nerve render, okay? And then we're going to add noise to it, and then make a noisy image, and then concatenate this with the original input image, which is the input to Instruct Pix to Pix. Send it to Instruct Pix to Pix with your instructions, and the Instruct Pix to Pix will denoise this image to the required instructions. And then you're simply going to replace that image in the data set with this denoise image. Okay, and you're going to do this in an iterative manner, as in you're going to take one image, update it, and then you're going to do n equals 10 steps of nerf update, and then you're going to repeat this. An easy baseline that you can think about is take all of your nerf images and then apply Instruct Pix to Pix on every single image of it, and then run nerf. That would be a baseline. But that method I will show you, but we'll give you inconsistent types of edits because there are many different ways to turn this bear into a grizzly bear. The nice thing about this iterative dataset update is that, a single image is updated slowly. So the nerf slowly adds content. I can show you. So as time goes on, you can see that the images are slowly getting updated. And because the update is conditioned on the current nerf render, which incorporates the slowly changing content, this way it can actually preserve continuity and consistency across the different views. And this is just like the SDS interpretation that I told you, because if you're replacing your input image with the denoise image, you're literally guiding your nerf to look like that denoise image. And it's going to be semi-permanent. You're still going to update it as you go. So here's some more videos of training progression. So as you train your nerf, especially the one on the right, where we're trying to make him into an elf, you can see that the ear is slowly growing to the final shape. Yeah. Okay. So here are some more examples. We can also do whole bodies. And this is a good baseline. So the results shown in the middle, oops, the text is off, but is the running Instruct Pix to Pix in a per frame manner. And you can see that there's just really many ways to turn a person into a clown. And so that's going to be really inconsistent, right? And then so the thing on the right is what consolidating this in a 3D space gives you. Here are some more results on the scene. So this is the original nerf inputs. We can make it into a sunset. The sunset is probably one of the best. We can also make it look like a desert. We can also make it look stormy. And then this one, make it look like it just snowed. I think this is a cute failure case because Instruct Pix to Pix really didn't want to put snow around the green part. So I'd say this is like a California snow. And here are some more examples of the method. Now, this isn't really perfect. If you look at the panda carefully, you see this bas relief ambiguity effect of the fact that the black part of the eyes, or it's due to really inconsistencies in the edits. But it is still giving a reasonable edit. Then let me compare it to the ablations. Okay, so ours is ours. The one-time dataset update is a simple baseline where you simply replace all of your training data with one go of Instruct Pix to Pix with the same prompt. And you can see that this isn't terrible, but all the inconsistencies are accumulate as a floater around the cameras, because things you cannot describe by a consistent nerf, the nerf likes to put it in front of the camera such that when you're reconstructing that particular frame, it still minimizes the training loss. The thing on the right, bottom right, hours plus stable diffusion is a method without instructions. You do the exact same thing, oops, but stable diffusion, ooh. Okay, we can move on. The stable diffusion requires you to textually describe the image. And so that's why it's really hard. And then you still see the resemblance because you're always adding a noise from the current render. But this is really the instruction versus description. And then the bottom right is an STS and an instruct pix to pix. Basically, it's like similar, but the way in which you update is directly like an STS, where you're rendering a small image instead of updating an entire data set, which results in smaller resolution updates and like poor array sampling, and that results in not great results. Okay, here are some more comparisons. This is really a subjective task. The nerf art is actually optimizing a clip loss, and the one above is really more about image conditioning. And so I really think it's, both of them could be good if that's what you're looking for. Because this is an editing, we allow, just like in instruct pix to pix, users can choose the hyperparameters to specify their edit. We also do the same, but all of the 3D hyperparameters are fixed. So the way it goes is like user uses instruct pix to pix, wants the edit, now that's fixed, and then you apply your 3D editing. Okay, so one of the limitations of this approach is that, it's of course upper bounded by the capabilities of instruct pix to pix. Like you saw in the case of it cannot do really, really strong updates. For example, if you say delete the bear statue, it cannot really do that. And so we can't also do that edits. In some cases, instruct pix to pix can achieve the edit, but it does it in such an inconsistent manner that we fail to consolidate it in 3D. So for example, give him a checkered jacket, we'll give him a checkered jacket, but the particular pattern of the checkeredness of the jacket is different in every single frame that, the 3D really just averages that. So as these approaches get better and better, I'm sure we're going to get much better edits and also better ways of ensuring consistency. So the code is out for this one, and this is super exciting because somebody just used it to our codes to make them into a Hulk, which I think is really cute. It's also implemented in Nurse Studio. Okay, so I think I have like 8 more minutes, and using time, I want to talk about this other new work that we just put on archive. So the idea is same, but now the domain is slightly different, and now we're using a 3D diffusion model. So this is called Generative Proxemics, a prior for 3D social interaction from images, led by Leah Mueller, who was visiting my lab from Max Planck, along with my student Vicky and George. Okay, so people are social creatures, and we really like to interact with each other, but the existing methods for single human predictions, single image predictions really fail to capture the subtle nature of social interaction. And they don't really look that great because it's really lacking in this idea of how people interact with each other. Okay, and then, it's really not just about resolving intersections, because you really need to, subtle angles of your chin looking forward, or like the way your hand wraps around people are really important cues. And so this is why we really need a prior for proxemics. And what is a proxemics? Proxemics is a fancy word for saying the way a person positions themselves in relation to others. And in this work, we present Buddy, which is the Buddy's diffusion model, a data-driven prior for 3D social proxemics. So what is it? So basically, we learn a diffusion model on the joint distribution of humans in close proximity. So these are actually samples from our model. And in order to train this, you need data. So what do? We take images, and then there's this nice data set by Ferraru et al. That actually has these people in contact with contact labels. And so humans went in and said that this body part and that body part are in contact. With this, using this as a label of contact map, we can take some optimized predictions of the current estimate and then minimize, do an optimization problem to minimize this contact satisfaction. Okay, once you do this, you get quite a reasonable contact information compared to the starting point. And, they can, so now, this is a Flickr, so it involves a lot of sports data too, but they look quite reasonable. And so basically what we do is we're going to create pseudo ground truth using these 2D image data set. And then we're going to then train a 3D diffusion models on the underlying parameters. So specifically, without getting into the details of the human body model, let's say there is person A and person B, and there is global orientation of this person, local pose, shape, like a height parameters, as well as their translation with respect to each other. And then you can concatenate this into XA and XB, and then you train a diffusion model directly on this. And we did it in the simple space directly instead of joints because, contact really requires reasoning about surface and the height of the other people. And so you really train this like a normal body, a normal diffusion model, but here's a visualization of just adding random noise into simple parameters, which gives you these like messed up people. And then you really train to denoise this. And so this was quite, our experience was that it was quite easy to train this. I mean, we didn't have to fiddle too much. And so we were really impressed by the easiness of the, to train a diffusion model. And it's a transformer-based architecture. Here are some samples, the meshes that are sampled from this. And of course, there is, I can talk about the pros and cons later. Anyway, now that you have this as a prior, at test time, previously you needed these contact labels, which is quite expensive and challenging for humans to obtain. Now we can go away with the contact label and then use the diffusion model as the prior in your optimization. And we do it exactly the same way that I described in the beginning, basically alternate notation of basically the dream fusion in SJC, where you're really guiding your current parameters with the denoised values. So that's really what we do, and then do the optimization with it. And so here is on the left, optimization with the diffusion model, and on the right is heuristics. Of course, there's still some issues like intersections, but it can really capture this more subtle information between people. And of course, we also try to do this with other types of generative models like VAEs, but they tend to also not be as expressive. This is a really challenging joint distribution to model because your height and the distance really influence each other as to how much you should move. And really the iterative aspect, I think, of the diffusion model really helps to get the right thing. So here are some of the issues. The heuristic really just puts together the closest point together. It's trying to kiss, but then the kissing is, out of distribution data, but it's getting there. It's looking at each other. Yeah, so here are some results. And in the interest of time, I'm going to skip all of the results. Here are some of the results and get to the summary, which is that you can really use diffusion models like a prior in many 3D tasks or inverse vision problems. And today I showed you two examples, one that uses a pre-trained 2D diffusion model like instruct pix to pix, and 3D diffusion models that we've trained on our own. Of course, there's pros and cons in each. We also have another paper where we explore this called Nerf Busters, where the goal was to remove these artifacts from nerfs by learning a tiny 3D diffusion model. It's like an eraser that you can go and erase things. There's really an interesting discussion in the community as like, should you really use 2D generative models or 3D generative models? I really am a fan of learning from 2D images. So I really think actually images are the abundant things. Like even in this body, we try to learn the generative prior from images, right? So we just reconstructed it into 3D and did the diffusion generative model in 3D. That has a benefit because that is the parameter that you want to optimize. But I really think for the data reason, I think the 2D diffusion models are a way to go. But this is an interesting topic in a panel discussion. And it really is an exciting time where we can do all of these things. So I'd like to thank my collaborators and my students. Ayan is a first-year undergrad in this project, and really Matt and Alex really helped them a lot. And then Leah and Vicky and George and Michael have done a great job in this Proxemics project. Okay.
Thanks a lot. We have time for maybe two or three questions from the audience. Kunhao is waiting over there. I have one, and I'll let other people think about. your first project, how much geometry can it actually add to the like the instruction of the nerve? I mean, it can make the ears a little bit longer, but could it also like make the nose like a Pinocchio nose very long?
Yeah, no.
Is there like a
Interesting
limitation?
question. Yeah. No, so I think it still suffers from the issues like Dream Fusion cannot also do like really big changes because it will create these like multiple faces from different directions. So it'll have that kind of issues. So like, so if you look at this video, you can, it will also add like that nose became circle. And then like, you know, the hair became, it's also, you can remove the hair or add cowboy hats, but in certain object is quite hard. It's really just a Dream Fusion problem. And so that really is yet another challenge.
And dynamic scenes, have you thought about that?
Of course, dynamic scenes is the way to go. It's a very challenging problem and we're working on it.
Okay, got it. Yeah. Good. You can also shout.
Yeah, I think my question is pretty related to previous one. So in this editing, it seems like it's mostly about a texture or the like more like a surface editing. I wonder, is it like how does this kind of technique perform if I'm going to remove or insert the entire object in the 3D scene?
Yeah, okay, so removing an object in nerve is actually not that bad because removing a density is quite easy. Other works have shown this too, and like in this particular example, you're also removing like hair, right? So removing is much easier than inserting an object. Inserting an object is really hard because you have to make something out of nothing, and making it consistent is challenging. And in this work, the key is that you actually have a starting off with a scene that is consistent. And so editing a surface makes it more easier. And that's really the kind of story.
Okay, for the sake of time, we are going to stop here. Thanks a lot, Angjoo. Fantastic talk.